Swayam Prabha. Digital India. Educated India.
In the previous lectures, we studied operation of bipolar junction transistor. We kind of went into the device physics a little bit, and then we created the models in large signal model, a small signal model of the bipolar junction transistor. In this particular lecture, we will start doing bipolar junction transistor circuits. Now in this lecture, I'm going to teach you how to step by step figure out which mode of operation the bipolar junction transistor is in, and then which model we should use for analyzing the circuit. We will do it for NPN devices in this lecture, and in my notes I'm going to provide you with the PNP analysis. So please do that analysis by yourself so that you are comfortable. So we'll start with the DC analysis for bipolar junction transistor. Initially we will start with NPN, and this example I have created is specially formulated such that we can put the BJT through different regions of operations, and it will be clear as we go along. If you're studying by watching this video, please draw the schematics on a piece of paper or in your notebook and follow the example by solving it yourself. So the first thing you need to do when you're working with bipolar circuits is figure it out which region of operation the transistor is working in. In this particular case, since I haven't taught you how to make that quick judgment, let's go step by step so you can understand the thought process. The first thing we will do is we will ignore the base current in this particular circuit, which is going to flow here, IB. We are going to ignore that, and we're going to look at the what is our base to emitter voltage looking back if we ignore the base current. Okay, and you will quickly be able to tell that the V base to emitter is going to look like 2K divided by 80K plus 2K multiplied by 5 volts, and this is going to be equal to 0.122 volts. So it should be obvious then that the base to emitter junction diode is not going to be turned on. Okay, and as a result of which we can say that the transistor Q1 is off, and if Q1 is off, then there is no collector current flowing. So the collector current IC is going to be equal to 0, and if collector current is 0, then what is the output voltage? V out is going to be equal to 5 volts because IC is equal to 0. So this is the simplest example where the transistor is off, and that is happening because of this particular resistor. That number is small. So let's redo this example. In this example, we will just change the value, this particular resistor, to be equal to 20K. So following the same method we did before, we can quickly tell that if you ignore the base current, then the voltage looking back here is going to be 20K divided by 100K, which is 1 volt. So there is a good possibility that the Q1 can be turned on. Now let's get into the details. First thing what we will do is we will look at Thevenin's equivalent looking back this way. So refreshing your memory, if you have two resistors like this and you have 5 volts, then this Thevenin's equivalent is going to look like a voltage source VTH and a Thevenin's resistance RTH. What is the value of VTH? We will look at the open circuit voltage looking in here, and that is going to look like 1 volt. RTH value is going to be, we will take the independent voltage source of 5 volts to 0, and we will look at equivalent resistance into this network, and that would be 20K parallel with 80K. So this would be equal to 20K parallel with 80K, and this number is 16K ohms. Now I can draw the circuit again, and it's going to look like this, and we will assume VBE on for the bipolar transistor equal to 0.7 volts. This is 1 volt. We can safely assume that we can have the bipolar base emitter junction is turned on and VBE equal to 0.7 volts. As soon as we know that, we can tell the current which is flowing through this resistor, which is going to be our IB, and that current is going to be equal to IB is equal to 1 volt minus 0.7 volts divided by 16k ohms, which is equal to 18.75 microamps. Now we will assume first is that the transistor is in forward active region, and then verify if our assumption is correct at the end. If you assume it's forward active region, then we know the beta is going to be 100. So IC is going to be equal to 100 times 18.75 microamps, which is equal to 1.875 milliamps. Let me redraw the circuit again with all the details. As I said again, IB is equal to 18.75 microamps and IC is equal to 1.875 milliamps. What is the value of output V0 DC voltage? You can quickly tell that the DC value at V0 output is 5 volts minus IR drop across this particular resistor, which is given by 1.33K multiplied by 1.875 milli. If you do this calculation, it will come out to be exactly 2.5 volts. Now we have to verify what is the status of base to collector junction. Why are we doing that? Since we assumed in the beginning that the transistor was forward active, and what is the rule for forward active region? Base to emitter junction is forward biased and base to collector junction is reverse biased. If V0 is equal to 2.5 volts DC, then the base to collector junction equal to minus 2.5 volts minus 0.7 volts, which is equal to minus 1.8 volts. So we can safely say that this transistor is in forward active region with base emitter junction forward biased, base collector junction is reverse biased. Let's now put out the DC operating point with all the numbers here. The current through 20K is going to be 0.7 volts divided by 20K. That would be 35 microamp. The current through 80K will total current 35 plus 18.75 microamps, and that would be equal to 53.75 microamps. Current here is going to be 1.875 milliamps. What is the emitter current? Emitter current is summation of this base current and the collector current, and that would be equal to 1.893 milliamps. That's your emitter current. So this is something called, we already learned, it's called DC operating point of the transistor, where we are meeting all the requirements or conditions of operation of the transistor in a proper region of operation. So for example, if you simulated this circuit using SPICE simulator, then you would see these numbers at different nodes and different, you will see these currents in different branches. So our job of DC operating point is now done. Now we will figure out how does this circuit behave as an AC circuit. When I apply a small signal voltage, then how does it work? One point I would like you to know that we cannot just connect a AC voltage source right at this point, V in AC. The reason for that is, if you are applying a AC voltage source like this, then the DC value at this node will become equal to 0. And the transistor will cease to operate in the region that we want it to operate in, and it will be cut off. So typically what you would really like to see is, you would like to see a DC voltage source in series over here. So this would be your DC biasing. This would be VDC input. And this VDC input has to be same as our original operating point, which is equal to 0.7 volts. In reality, we don't do it this way. Specifically, if you're looking at audio frequency signals where you're not worried about the DC, you're not worried about passing DC through your circuit, then we use capacitor. So this will be a big capacitor which will be put in there. So this would be C big. If you use C big, then you don't have to have the DC input source here. So C big will isolate the DC between the two circuits. And generally this VN will be coming in from the previous circuit, which is going to drive our amplifier. The capacitor C big helps you in isolating the DC operating point of each circuit, rather removing loading of one circuit, the following circuit, in terms of DC operating. However, from the AC point of view, this C big can be looked at as a short. We choose the C big based on the frequency of operation of the circuit. Now we would like to do AC analysis of this circuit. For AC analysis, we know that we will connect all the DC voltage sources to 0. And in this particular case, we will short the C big, because for the frequency of operation, C big is a large value capacitor, so it acts as a short, and it only acts as a capacitor to block the DC. So let's draw first we know the transistor Q1 is in forward active region. So the small signal model for the forward active transistor is like this. So this is the small signal model of the bipolar transistor operating in the forward active region. Just to make a point, collector to emitter current is given by GM V pi, where V pi is the voltage drop across VBE. Again, all these quantities here are small signal quantities. Using our DC operating point, we figured out what is the value of R pi, what is the value of GM, and what is the value of R0. R pi is beta over GM, GM is IC over VT, and R out is VA over IC. IC is the DC operating point current flowing through the transistor, collector current of Q1. So these are all from DC operating point. Now we will put in rest of the devices or rest of the elements for our AC analysis. As I said, the resistor, let's call this R3, is connected from output to 5 volts, and 5 volts we are going to connect it to ground for the purpose of the AC analysis. So here in this case it would go from collector to ground. This would be R3, 1.33K. The resistor R1 and R2, which were 80K and 20K. Once again, since we connect 5 volts to VDD to ground for the purpose of AC analysis, it would look like there will be two resistors, 80K in parallel with 20K, and they would look like this over here, and that would be 16K. And as I said already, C big we are going to connect with a short for the AC analysis purpose, because for the frequency of operation we are analyzing, it looks like a short. And the last thing we will have is the AC VN, and the collector node will be your output voltage, and emitter node is connected to ground. So this is our detailed AC analysis circuit. It still looks like there are a lot of components, but we can do quick calculations and figure out which ones are important and which ones are not important. Let's calculate the value of R pi, GM, and R0 based on our previous analysis, the DC operating point. So GM is given by IC over VT. GM is given by 72.115 milli Siemens. Siemens is reciprocal of ohms. R pi is equal to beta over GM. That would look like 100 divided by 72.115 k ohms. That will be equal to 1.387 kilo ohms. Output resistance R out is given by VA divided by IC, which is equal to 100 divided by 1.875 kilo ohms, 53.33 kilo ohms. So we know all the values that we need, and we need to figure out what the gain of this particular configuration is. One quick thing to note here, just by inspection, that I would like to show you is, if you look at the resistor of 16K and if you look at R pi, they are appearing directly across input voltage source. So they don't really participate in the transfer function, because if you look at V in, that is same as V pi, and this V pi will get replaced by V in. Okay, so that's the observation. Of course, 16K and R pi value of 1.387K are important because they are going to load the previous stage. But for purpose of this particular example, we are using Vin as an ideal voltage source to drive this circuit. And as a result of that, 16K and R pi will not contribute to our transfer function. Just by using Kirchhoff's laws, you can say that the circuit now boils down to a simple configuration that looks like this. So if I have to do a back of the envelope calculation, I can quickly tell that R out is much larger than R3. So we can safely ignore R out and we can figure out the gain V out is equal to minus GM times V in times R3. So the gain will be equal to minus GM times R3, 72.115 milli multiplied by 1.33K, and this is going to be equal to minus 96.15. What does minus sign indicate here? Minus sign indicates inversion. What that means is if I'm applying a positive going voltage over here, then we should see voltage that looks like this, inverting. And the gain of 96 is telling you that if I apply a 1 millivolt signal here, peak, then I should see at the output approximately 96.15 millivolts at the output. So you can certainly see there is a large gain using a bipolar transistor we can get, and we can even get higher gain. Another point I would like you to notice here is DC output value of the output voltage. If you remember, when we did the analysis, the output DC value was 2.5 volts. Now there is a specific reason I chose that value to be 2.5 volts. If you look carefully, the output voltage can range from 0 volts to 5 volts. Because 5 volts, because it's a supply. We have biased the output of the amplifier by choosing proper R3 value to be equal to 2.5 volts. So when you don't apply any signal, this would be the DC output voltage at the output of our amplifier. Once we apply the signal, as we said, we get inverting output, we will get something that looks like this, a sine wave that looks like this. Now it will be obvious to you that the 2.5 volts is advantageous because you have equal amount of space to go up and down. You can amplify the signal without clipping to a large value because of by choosing 2.5 volts. We know that as we go close to 0 volts, the transistor will be going into saturation. So something like 0.2 volts clearance from 0 volts. But for all practical purposes, we can say that the output voltage can swing from 0 to 5 volts. So there'll be full rail-to-rail swing is what we call it at the output of the amplifier, with the caveat that 0.2 volts clearance from 0 volts. And that is because the transistor Q1 here will go into saturation. And we also know that the gain is given by GM times R3, which is the biasing resistor. R3 is the biasing resistor. So I can increase the gain by increasing R3. If I increase the R3, then the DC value here, which was given by IC times R3, will keep increasing. So this will look like, it will look like this. So this would be different R3 value. And you can quickly tell that my signal, output signal now will clip as I go down, but it will not clip on the other side. Hence we choose the output DC voltage to be at the mid supply range. I hope this point is clear. Now we will repeat the same example as before, except for one change. And in this particular change, I am going to increase the resistor R3. Originally we had it to be 1.333K. I'm just going to move the decimal point to the second spot. So it's 13.33K. That's the only change I have done. And let's analyze what happens in this circuit. So nothing has changed at the input. So the input will be will look still the same. We know that the VBE will be equal to 0.7 because the transistor base emitter junction is forward biased. We go back to the same method again, step by step. This is our Thevenin equivalent of 1 volt and this is our 16K. We are back to DC operating point. So we are doing DC analysis or a large signal analysis right now. So this was 18.75 microamps and this was 0.7 volts. Same as before. If the transistor Q1, we can continue to assume is to be in active mode, then IC will be equal to 100 times base current, which is 1.87 microamps, and this will be equal to 1.875 milliamps. What is the value of DC voltage at output Vout? DC is going to be 5 volts minus IC times R3. What is the value here? This is going to be 25 volts. So Vout DC is equal to minus 20 volts. So this is telling us that something is not right about our original assumption, because we cannot have minus 20 volts. Our transistor is biased from 0 to 5 volts. This is telling us that active mode assumption is not correct. So from that we can tell that the transistor Q1 is going to be in the saturation region. Kind of tells you that the output voltage is going down and is going towards ground, which in a way tells you that VCE, you will hit VCE somewhere close to 0.2 volts, and that would be the lowest you can go to. So let's figure out what's going to happen in the saturation mode now. So since we assume the transistor is in saturation mode, then the output voltage will be somewhere close to 0.2 volts depending upon level of saturation. If it's at the borderline of the saturation, then we say it's maybe 0.3 volts VCE. This is VCE, collector to emitter voltage. Now let's figure out all the currents. So first of all, what is the collector current? IC. We said VCE is equal to 0.2 volts approximately. Then IC is equal to 5 volts minus 0.2 volts divided by 13.33 K. And this number comes out to be 0.36 milliamps. So of course this current is less than 1.8 milliamps that we had calculated. IE, emitter current, is going to be equal to 0.36 milliamps plus base current of 18.75 microamps, which will be equal to 378.84 microamps. Since we have assumed output at 0.2 volts, then the base emitter junction is going to be base emitter VBE is equal to 0.7 volts and VBC is going to be equal to forward biased, and it will be approximately 0.5 volts. So both the junctions are forward biased. Let's draw the large signal model for the transistor in saturation region, and then we can figure out the currents in each branch. So this was our original active mode device DC circuit. Since we have base to collector junction also forward biased, then as we learned before, we will draw another diode here which is forward biased, and that looks like this. So we know that the base current is 18.75 microamps, and there is current IB which will flow through your VBE diode, base emitter diode, and 100 times IB will flow from the collector. We know the collector current is 360 microamps. So first, Kirchhoff's current law at the base node will give us current flowing through the base collector junction diode forward biased is going to be equal to 18.75 microamps minus IB. So let's solve these two equations. Collector plus 360 microamps is equal to 100 times IB. So we can say 101 times IB is equal to 378.84 microamps, and IB is equal to 3.75 microamps. So our final DC operating circuit for the transistor in saturation will look like this now. So in this case, we have specifically shown, since this is your DC op circuit, we have 5 volt supply, and this 1 volt is Thevenin equivalent due to the voltage divider at the input. And as we derived earlier, the currents will look like this. 18.75 microamps will flow through this, and the base current is going to be equal to 3.75 microamps. And 100 times that will be 375 microamps flowing through the and there will be 0.2 volts drop here, VCE. This is our collector, this is the base region, and this is the emitter region. Okay, and as we already said, this is 15 microamp, and the total collector current will flow is 360 microamps. So this is the way to analyze a transistor in saturation mode, and again, this is a DC operating point, large signal analysis of the transistor. You have to make sure that you distinguish between this and the small signal operation of the transistor. During the small signal analysis, we use a different model, the linearized model. We will connect all the independent sources to 0. So VDD will go to 0. Any kind of DC voltage source in the circuit, that will go to 0. In the lecture notes, I would like you to go through, follow the same exact example for PNP transistors. That will make you more comfortable. Pretty much what we have gone through today is with one simple example. I have taken you from transistor which is totally turned off to transistor which is in active mode to transistor which is in saturation region. And our most favorite mode of operation is going to be the active mode, because that's where we are able to get small signal gain from the device. That's to keep in mind. So what we do is we do a large signal analysis and figure out which mode the transistor is going to be. Make sure that all the terminal voltages and current conditions are met. And based on the large signal analysis, we figure out the small signal parameters. And the small signal model is what we use to figure out the small signal gain of the amplifier. Thank you.